Ask a 7 billion parameter model a question, and the answer streams back almost instantly. Ask a 70 billion model the same thing, and you wait 10 times the parameters and roughly 10 times the weight. And here's the thing, it's not because the bigger model's logic is somehow harder. Every single token it writes costs thousands of massive matrix multiplications. Today we look at that one operation, the math behind why size equals slowness. Peek inside a running language model and you find something strange. There are no loops, no if statements, no branching logic of the kind you'd write in code. It's just matrices hitting matrices billions of times over. The entire output, every word it picks, is shaped by one operation, matrix multiplication. Here's the whole idea in miniature. A 3 by 3 matrix, A, times a 3 by 2 matrix, B. To get the first cell of the answer, you take one row from the left, one column from the right, multiply the pairs, and sum them, that gold cell. That's it. One row, one column, one result cell. A single multiply and add. Now scale that up. In a real model, these grids are 10,000 by 10,000, and you do thousands of these multiplications for every single token. That's where the time goes. In the next 15 minutes, 3 things. First, what a matrix actually is, and why. Inside a neural net, it's really a transformation. Second, why size equals slowness, why more parameters literally means more multiplications. Third, we trace a single token, hello, through a real weight matrix step by step. By the end, you'll know exactly why your GPU is screaming when you run inference. So, what is a matrix? At its simplest, just a grid of numbers and rows and columns. That's the whole definition. Nothing scary. We describe its shape as rows by columns. This one is 2 rows, 3 columns, a 2 by 3. But inside a neural network, a matrix isn't just storage. It's a transformation. You feed a vector in, and it hands you back a new, reshaped vector, rotated, stretched, projected into a new space. And those numbers filling the grid are the weights, the exact values the model learned during training. The matrix I is the knowledge. Let's make transformation concrete. Here's an input vector, say the embedding for a word, about to go into a weight matrix W. Out comes a new vector. Same idea as a function, input in, output out, but it acts on a whole list of numbers at once. Geometrically, W can rotate it, stretch it, and project it into a space that's more useful for whatever comes next. And notice, there are no handwritten rules anywhere. It's purely numbers multiplied by numbers. That's all a layer does. Now, the operation in LLM runs constantly. A matrix times a vector. Weight matrix W times an input vector X. We go one row of W at a time. Row 1, 0, 2. Paired with x2, 1, 3 multiply matching entries and add, that's a dot product straight from video 1. It gives a first output number, 8. Row 2 with x, another dot product, gives 4. Row 3 with x gives 9. The output vector fills in 1 entry per row. So matrix times vector is just a stack of dot products, 1 per row. Hold that thought. It's why this gets expensive. Scale once more, matrix times matrix. Matrix A, 2 by 3, times matrix B, 3 by 2. Why multiply 2 matrices? Because you rarely transform just one vector. You transform a whole batch at once. Each column of B is its own vector. Top left cell, row 1 of A120 dotted with column 1 of BB201 equals 2. Row 1 with column 2 of B gives the top right cell, 3. Row 2 with column 1 gives the bottom left, 3. Row 2 with column 2, the bottom right, 1. Every cell of the answer is one dot product, a row from the left, a column from the right, same move, repeated across the grid. Let's actually feel the cost. Each cell of the answer is one row, dotted with one column. Here's a real one. Row 2, 1, 0, 3, dotted with column 1, 0, 2, 1, 2 times 1 is 2, 1 times 0 is 0, 0 times 2 is 0, 3 times 1 is 3. Add them 5, that's one cell. Do another, 1, 2, 1, 0, against the same column, 1 plus 0 plus 2 plus 0, that's 3. 2 cells down. Keep going and the whole 4x4 lights up 16 cells. 16 cells means 16 separate dot products, each its own chain of multiply and adds. Now scale it. A real 10,000 by 10,000 matrix is 100 million of these dot products for every single token. Now the formula, and you've earned it because you've already been doing it by hand. Row 1, 2 dotted with column 3, 4, 1 times 3 plus 2 times 4, 11. Textbooks write that exact operation as a piece of shorthand. Cij equals the sum over k of aik times bkj. And here's the secret to never fearing it. Every symbol maps to the picture you just drew. Cig is the cell you're filling. The big sigma just means add up the pairs. That is the dot product. Aik is row I. Bkg is column J. That's the whole thing. Same move you already know. So forget the subscripts. Keep the picture, a row dotted with a column. 2 practical rules before we step inside a model. First, the shape rule. You can only multiply A by B if A's columns match B's rows. The inner numbers must be equal. When they match, the answer shape is the outer numbers. A 2 by 3 times a 3 by 2 gives a 2 by 2. If the inner numbers don't match 2 by 3 times 2 by 2, the multiplication is simply undefined. Shapes are everything. Second, the cost. The number of multiply adds is roughly rows times columns times that shared inner dimension, 3 numbers multiplied together, which means doubling every dimension doesn't double the work, it roughly eightfolds it. Size punishes you fast. So where do these live and how big are they? It starts with the embedding matrix for a 7 billion model, roughly 32,000 by 4,096. Vocabulary size by model width. Attention needs 3 weight matrices per layer, WQ, WKey, WV, each 4,096 squared. That's about 16 million numbers apiece per layer. Then the output projection, WO, same 4,000 square. The feed-forward network is the heavyweight. 1 is 4,096 by 11,000, and W2 is its mirror. These are the biggest matrices in the model, and they dominate the compute. And an unembedding matrix at the end, width by vocabulary, turns the final vector into a score for every possible token. Stack that whole block around 32 times for a 7B model, 80 plus for a 70B. Those dimensions, multiplied out across every layer, are the parameter count. Picture the model as a tall stack of these blocks and a token flowing straight down through all of them. The width of the model is how big each matrix is, the dimension of the vectors. The depth is how many layers you stack, often 80 or more. Total work per token is depth times the matmoles in each layer. Both knobs multiply the cost, and none of it is skippable. No early exit, no shortcut. Every token runs the entire stack, every single time. Now we can answer the opening mystery. That 7B label means 7 billion numbers, filling all those weight matrices. 70B means 70 billion, 10 times as many entries in the grids. And every entry is touched by the multiply adds on every token. More entries, more arithmetic, there's no way around it. Roughly, each token costs about 2 floating point operations per parameter, so 7 billion params is around 14 gigaflops a token, and 70 billion is about 140. 10 times the operations, 10 times the latency. That's the whole reason the bigger model is slower, not smarter struggling, just more multiplication. 1.2 seconds versus 12. The size, made of matrices, is the weight. This is why language models run on GPUs, not regular CPUs. A CPU does a handful of multiplications at a time. A model needs billions per token. A GPU is built for precisely this. Thousands of multiply and adds in parallel, across enormous grids. So the raw math is fast. Which means a 70 billion model should still feel quick, right? Here's a myth worth busting. GPUs are fast, so a big model should still be quick. Wrong. The bottleneck usually isn't the math at all. It's the memory highway. Think of the GPU as a Ferrari, and the weights as fuel at a gas station across town. Every single token, the car has to drive over and haul all the weights back before it can compute. Real numbers. A 70 billion model in half precision is about 140 gigabytes of weights. A top-end A100 holds 80. 140 is bigger than 80, the model doesn't even fit on one chip, and every token has to stream all of it through. That's why inference is memory-bound. The Ferrari sits idling at the pump, waiting for fuel. The math was never the problem. A quick aside on why we even build the slow giants. Plot model size against error on a log-log scale, and the points fall on a remarkably straight line. It's a power law. As parameters go up, loss predictably comes down. Those extra billions of matrix entries genuinely buy better answers. But here's a second myth to retire. Bigger is always worth it. The curve bends. Each doubling of size buys less and less improvement per dollar. Returns diminish. So it's a three-way trade-off. Bigger means higher quality, but slower and more expensive. You can't max all three. Every model you use, and every serving decision behind it is a point chosen on that curve. Now the real thing, let's trace hello through a weight matrix with actual numbers. One token. Step 1, the embedding lookup from video 1, hello, becomes a vector 0.7, 0.1, 0.9. Step 2, it meets a weight matrix W, a real 3x3, with learned values like 0.5, minus 0.2, and so on. Row 1 dotted with the vector, 0.5 times 0.7 is 0.35, minus 0.2 times 0.1 is minus 0.02. 0.1 times 0.9 is 0.02. 0.1 times 0.9 is 0.09. Add them 0.42. That's the first output number. Row 2, 0.21 plus 0.08 minus 0.36, that comes to minus 0.07. Row 3, minus 0.07 plus 0.06 plus 0.18, 0.17. Stack those three results and hello is now a brand new vector, 0.42 minus 0.07, 0.17. And that was just one matrix. A single transformer block uses around 6 of them, and the model stacks roughly 80 layers. So that's on the order of 480 matrix multiplications for this one token. The thousands per token from the opening, now fully visible, every multiply accounted for. Let's lock it in. 1. Matrix multiplication is the operation inside an LLM, not loops, not logic, just rows dotted with columns. 2. A model size is the number of entries in its matrices, and that directly sets the compute and the latency per token. 3. At inference, moving those weights through memory is often the real bottleneck. The GPU waits on data. In video 1, distance in space was meaning. In this one, transformation is a matrix, and those vectors are exactly what these matrices act on. You just learned matrices and matrix multiplication, the engine, and the bottleneck of inference. Next up, softmax and temperature. How the model turns that final pile of numbers into an actual word, and what the temperature slider really does. This is video 2 of 7, and each one builds on the last. Follow the series, and I'll see you in video 3.